All right. Well, welcome back, folks. I hope everyone had a nice break. Hopefully, you were able to rest a little bit. Looked like about more than half of you were able to keep up with the videos that I posted for you over the break. We tried to get as far as we could with the Chapter 9 material, and I think we did get pretty far. I would like to get started with hopefully, we can try to get started with the molecular orbital theory today. And that way then we can try to wrap up this chapter by the end of the week. Okay. For those of you who did not get a chance to watch the videos over the break, please make sure you get those video watched. Those videos have no work associated with them. Basically, they are presenting you information from Chapter 9, but you do need to know that information in order to keep up with what we'll be doing here. So what I would suggest you do then is before you watch this video, try to go ahead and watch those videos and get caught up. What I'll do is I will make the work associated with this particular lecture here. I'll extend the due date for those of you who need to get caught up, but please, and I'll make it due by the end of this Friday for the lecture material. But please make sure you get it done and turn it in. You need to make sure you know about hybrid orbitals and what hybridization is, about the three types of hybridizations that we've talked about so far that you do need to know: the sp, sp2, sp3. We talked about dsp3 in the last lecture. And remember, I did tell you, you won't need to know that for the AP exam, but the AP exam will definitely ask you about hybridization, and make sure you're able to make sure you're able to trace the relationship between hybridization and molecular structure, because that's absolutely important. So the VSEPR theory that we finished up with back in chapter 8, make sure you're able to do that and practice it. Again, keep practicing it with the PhET lab if you need to, but you'll need to definitely review that and know that for the discussion of hybridization here. Okay, so if you have any questions, please make sure you come by and get your questions answered. Okay, and that way then I can clarify some things for you. But the expectation on my part then is that you will be able to review the videos on your own. They're posted on Edpuzzle. They are there for you. Make sure you watch those videos, and then come by after school today, 1:30 to 2:30, to get any clarification that you need. But make sure you please watch those videos. Okay. All right, so let's go ahead, and I apologize for Friday. I had some issues with my laptop. I couldn't record the video on Friday, and so I apologize for that. We'll pick up with where we left off last Thursday, and we'll try to get done with it today. Okay. All right. So where did we leave off with on Thursday? We left off with this particular molecule here. Now remember, there were the different hybridizations that we talked about up till this point. Let's go ahead and I'll list those really quickly. We had sp hybridization. Remember, with sp hybridization, then we had a linear molecule with two sp hybrid orbitals here. So remember, it's going to be linear. Okay. Two sp, and this is going to be electron geometry. You're going to get two sp hybrid orbitals and two unhybridized p orbitals. We then talked about the sp2 hybrid orbitals, and the geometry there was trigonal planar. And with the trigonal planar geometry, then we had three sp2 hybrid orbitals and one unhybridized p orbital. And then we started out with the discussion of sp3 hybrid orbitals, which gave then a tetrahedral geometry. Okay, and these are the three orbital hybridizations that you will absolutely need to know for the AP exam. Okay, so you have the linear SP, the trigonal planar SP2, and the tetrahedral SP3. Remember, with the SP3 here, we have all four of these hybrid orbitals here. You have four here, and all these hybrid orbitals then are going to be degenerate, which means that they will be equal in energy. And then with these here, you'll have, with the SP2 hybridization, you have one unhybridized atomic p orbital that's going to be slightly higher in energy. And with the SP hybridization, you're going to have two unhybridized p atomic orbitals that will be slightly higher in energy as well. Okay. All right, so those are the three that you absolutely need to know. Okay. However, with that said, then these hybridizations then can only account for in this example, are two bonds. Okay, two bonds that form. Okay, here they can only account for three bonds that form, and here you can only account for four. What happens when you have a molecule that has more than four bonds? Okay. In that case, then we started talking about the DSP3 hybridization. And with the DSP3 hybridization, we had then a different geometry. Make sure you review that over over the video. Okay. And so with that DSP3 hybridization, then remember with this, then it provides us then with 5 hybrid orbitals. What happens here is the atom goes and hybridizes an s orbital, all 3 of the p orbitals with 1 of the d orbitals that it has. Okay, so with these particular atoms here that require DSP3 hybridization, it requires that because what it needs then is it needs to be able to form 5 different bonds. What these hybrid orbitals do is that these hybrid orbitals participate in bonding. Okay? And so we talked about from there, from that discussion, that we were able to talk about the type of bonding interactions that occur. So these are the hybrid orbitals here. We talked about the bonding interactions, and we had 2 types of bonding interactions. We had the sigma bonding interaction, we had the sigma bonding interaction, and we had the pi bonding interaction. Okay, and these basically tells us then how these orbitals line up with one another. So with the sigma bonding interaction, the orbitals then will line up in a manner that is linear. And with the pi bonding interaction, then you have the interaction with the orbitals line up in a side-by-side manner. Okay? And so that gives us the difference then between the sigma and the pi bonding. Okay? So these are the hybridizations. These are the bonding interactions. You need to make sure you know both of these as we progress forward. Okay? All right. And so we were able to explain how with the molecule that we saw earlier, how with phosphorus pentachloride, how the phosphorus pentachloride molecule, the phosphorus has to be DSP3 hybridized in order to get that done. Okay? But what happens then if you take a look at so that's the molecule here, phosphorus pentachloride. You have that trigonal bipyramidal arrangement here. So let's go ahead and write that down. We have a trigonal bipyramidal arrangement geometry, okay, with the 5 hybrid orbitals that occur from the hybridization of an s orbital, with the all three of the p orbitals and the d orbitals and the 1 d orbital here. Okay, so 3, 4, 5 hybrid orbitals that form. Okay, what happens then? And we looked at the next molecule. Okay, what happens then if you have a molecule that requires more than 5 types of interactions? Okay, okay. And so we saw then with a molecule like xenon tetrafluoride here. Xenon tetrafluoride has only 4 bonds. Okay, so xenon tetrafluoride has only 4 bonds. However, okay, and this is where we figured we were talking about on the discussion last Thursday. Okay, this is not a tetrahedral configuration, and the key reason why is that what I've emphasized here. Okay, that you have 2 unpaired electrons here. You have 2 unpaired electrons that are not equal in energy. When we discuss photoelectron spectroscopy at the end of this chapter, we're going to see then that these 2 here are not equal in energy. Now, if they are, that they are equal in energy, okay, and if they are equal in energy, then these 2 here are degenerate. They are degenerate with these orbitals here. So therefore, if we can think about this here, this can't be tetrahedral. This can't be sp3. The xenon can't be sp3 hybridized because xenon sp3 hybridization, like I pointed out in the previous slide, only gives you 4 degenerate hybrid orbitals. Again, degeneracy means then that these orbitals are all equal in energy, and any electron in those orbitals will also be equal in energy. So when we do the photoelectron spectroscopy of this particular molecule, we see then that all of these electron pairs here, the 4 bonding pairs here with the 2 non-bonding pairs here, they are all equal in energy. And so because of that, then the xenon cannot be sp3 hybridized, but it can't be dsp3 hybridized either. And the key reason for that is because if we have dsp3 hybridization, then you only have 5 degenerate orbitals, and that means then one of these electron pairs then will not be equal in energy. That can't happen either. Okay, so dsp3 hybridization, one of these pairs here will be higher in energy than the other one because it will be in a d orbital, an unoccupied d orbital, and the remaining 5 then will be in the dsp3 hybrid orbital. So with that said, then xenon tetrafluoride cannot be dsp3 hybridized either. Okay, so make sure you keep that in mind. And so how then can we explain? How then can we explain the hybridization of this particular molecule? And so please make sure you keep that in mind. Keep in mind the discussion here we have about how we know that xenon is not sp3 hybridized, even though it has 4 bonding domains. Okay? And it can't be dsp3 hybridized either. And so therefore, what we see through photoelectron spectroscopy, and I'll write this down real quickly. Okay, this is what a spectroscopic method that we refer to as photospectrum spectrum. Okay. Photoelectric. Oh, I'm sorry. I'm getting slowly getting back into the groove of things. Photoelectric spectroscopy. Photoelectric spectroscopy. So spectroscopy, which we refer to as PES. We can use photoelectron spectroscopy in order to determine the energetics, the energies of these electrons here. And so we will learn about this particular form of spectroscopy, and we'll talk about what spectroscopy is. But this is where using this technique here, we are able to determine that all 6 of these electron pairs here are equal in energy. And if they are equal in energy, then and they are degenerate, the orbitals that fill them, there has to be then 6 hybrid orbitals, 6 orbitals that are degenerate. And the only way we're going to be able to do that is if we hybridize the p orbitals and 2 of the d orbitals. And so we have then what is called dsp3 hybrid orbitals. That gives us 6 of the hybrid orbitals. All 6 of these will be degenerate, meaning they will be equal in energy. If they are degenerate, they'll be equal in energy, and each one of these pairs here occupies one of those 6 hybrid orbitals, all equal in energy. And again, photoelectron spectroscopy supports that this particular structure for our model, for our molecule here. Okay. Let's go ahead then, and let's continue on. Okay, and so there it is. Xenon tetrafluoride then is going to be dsp3 hybridized. Okay, and with that said, then we have the 6 electron pairs all occupying then 1 of the hybrid orbitals. Okay, and so therefore 4 of those pairs will occupy a bonding interaction between fluorine and the xenon, and the remaining 2 hybrid orbitals will be occupied by the non-bonding electrons in the lone pairs. And so the arrangement here, the geometry is going to be an octahedral arrangement for these atoms here, with each of these the bond angles here being about 90 degrees and a 90-degree angle between the lone pair and the plane here on which the fluorines lie. Okay, and so that's going to be the hybridization of xenon. Xenon then is going to be our D2 sp3 hybridized. Okay. Now, a quick question for you, for those of you who are able to do it, what's the hybridization of the fluorines? Okay, what are the hybridizations of the fluorines? Okay, so let's go ahead and answer that question. Okay, so how do we, and we can use this as a review for what we will be doing for what we did in the previous lectures. And so for those of you who did not watch it yet, please make sure you watch that. Okay, so let's go ahead then, and for our purpose, so let's count the electron domains. You have then 1, 2, 3, 4 electron domains around the fluorine here. Okay, 4 electron domains around each fluorine. Okay, so 4 electron domains. Okay, and with that said, then we have 1 bonding and 3 non-bonding. And hopefully this is all review for everybody, because this is from back in chapter 8. Okay. And so with that said, then, if we have a 1 bonding domain here, obviously the molecular geometry is going to be linear. We only have 1 bonding. So the molecular geometry is going to be a linear geometry, 180 degrees, which means then the 2 sides of the atom, the bond is occupied by 2 atoms. So we have a linear molecular geometry. However, since we have 4 total domains, the electron geometry here is going to be tetrahedral. Okay? And remember, it's going to be this that we're going to look at. We're going to look at the electron geometry to determine the hybridization. If the electron geometry is tetrahedral, that means then the bond angle between all of the domains is going to be about 109, which means then that's going to be sp3 hybridized. Okay? So that therefore, each one of these electron domains, each one of these electron pairs will be sitting in a sp3 hybridized orbital. Okay? And so if you take a look at this here, then with the fluorine, then you're going to have then a sigma bonding interaction between one of the sp3 hybridized orbitals for the fluorine with the one of the dsp3 hybridized orbitals for xenon. And so therefore we can draw a line between that. That means the bond here is going to be a sigma bonding interaction between the fluorine and the xenon. Okay. All right. So please make sure you come by and you ask about it. Okay. If for those of you who have not had a chance to watch the video yet. Okay. All right. So with that said, then this next slide then summarizes for us the relationship then between the bonding, and these are going to be when in the book they're referred to as effective pairs. These are the electron domains. So let's make sure you keep that in mind. So these are the electron domains that we've talked about. In a molecule where you have two electron domains, then you're going to have then a linear electron geometry. So the arrangement of electrons here refers to the electron geometry. Make sure you keep that in mind and remember the difference between electron geometry and molecular geometry. So therefore the arrangement of the pairs then will be linear, which means then the hybridization. If you have a linear electron geometry, the hybridization will be sp3. So this table here, and I would suggest that you use this table here to help you study and memorize this table for the AP exam. And really you need to know these three here. These here you will need to know as we progress forward, but the three hybridizations that you absolutely need to know, because you may see it on an AP exam, is going to be then the sp, sp2, and sp3 hybrid orbitals. Okay. All right. Very good. So let's go ahead and let's practice this then. How do we determine then the structure? How do we determine then the hybridization of an atom in a molecule? Okay. Well, let's go ahead and do this here. What I'd like you to do is take a couple minutes. For those of you who can do it, go ahead and draw this for us, and I'm going to go through this with you. For those of you who haven't done yet, try your best with this then, and then we'll work it out together. But there are certain steps you need to make sure you do then. What you need to make sure you do then is you make sure you draw the Lewis dot structure first for that particular molecule. Okay, so draw the Lewis dot structure first. Make sure you don't forget that. So draw the Lewis dot structure. That's going to be the first step. Okay. Once you have the Lewis dot structure, you want to go ahead and you want to look at the center atom here and determine the geometry, determine the electron geometry for the center atom. Make sure you count the electron domains, okay, and then from there, you can find the hybridization of that center atom. What I'll ask you to do also is find the hybridization of the nitrogen and the hybridization of the hydrogen. Okay? And so with that said, then from there we can go ahead and draw the structure. Go ahead and label go ahead and describe then whether the bonding is going to be sigma bonding or pi bonding interaction. Okay, and then we'll go ahead and we'll pick up with this in just a moment. Okay, so draw the structures, okay, and try your best with it, but only take a couple of minutes, and then we'll go over. Okay, so let's go ahead and let's get started. Okay. All right. Well, welcome back, you guys. Hopefully you were able to draw something on your paper, so make sure you include your drawing on the paper for submission today, and then we'll take a look at and then compare it with what I'm going to show you in just a moment. Okay, so let's go ahead and let's take a look at this. Okay, so there we have it. We have our carbon, we have our nitrogen, and we have our hydrogen. Okay, Lewis dot structure, and let's go ahead and draw this first then. So our Lewis dot structure for the for this particular molecule, then hopefully you recognize in the carbon is going to be the center atom, triple bonded to nitrogen, single bonded to hydrogen, and with nitrogen then you're going to have a lone pair here, because remember what we need to account for is 10 total electrons in this molecule here, 10 total valence electrons. You have 2, 4, 6, 8, 10. So this structure works here. We can go ahead and do formal charges if we need to determine then whether this the formal charges on here will show us then that this is the best structure that we have or not. But with the resonance here, you can draw some of the resonance structure, but this, if you were to do formal charges, this will be the best structure for hydrogen cyanide. Okay. All right. And so with that said, then let's go ahead and you notice here then that carbon has 2 electron domains. If it has 2 electron domains, then we see then that the geometry here is going to be linear. So it's going to be a linear geometry for the carbon, which means then it will be sp hybridized. Okay. Now, I asked you to do the same thing for nitrogen as well. Okay, so if you take a look at nitrogen, it has 2 electron domains as well, so it will also be linear. It will also have a linear electron geometry, which means then that nitrogen is also sp hybridized. So in this particular molecule here, the carbon is sp hybridized and the nitrogen is sp hybridized as well. Okay, all right, very good. And so I asked you finally to describe the hybridization of hydrogen, and that actually was a trick question because remember, hydrogen, all the atoms, it does not hybridize. So there is no hybridization here, no hybridization for the nitrogen. Okay, so no hybridization for the nitrogen. It only has an s atomic orbital. Okay. All right, so with that said then, what we want to be able to do is we want to be able to describe then the interaction. So now that we've gotten the hybridization of each one of the atoms, okay, and we've also described, and so the molecular geometry for this molecule based upon the carbon atom here then will be linear. Okay, so linear molecular geometry, but also linear electron geometry for carbon. Okay, all right, so let's go ahead then. Let's take a look at what we have here. Okay, so let's go ahead and let's take a look at each one of these. So there we have one of the sp hybrid orbitals. So this is one of the sp hybrid orbitals for carbon. So this is one of its sp. So there's one of the sp hybrid orbitals. To form this bond here, to form this bond between carbon and hydrogen, okay, we're going to see then that hydrogen does not hybridize, and so therefore it will have its atomic orbital. This is the s atomic orbital. This is the s orbital for hydrogen. Okay, so this is the s atomic orbital. This is an sp hybridized orbital, so make sure you know the difference between this. Hydrogen doesn't hybridize, so it's using its 1s orbital. So this is the 1s orbital from hydrogen, and so it has its electron right there. So it's going to have its electron in the 1s orbital. Okay, and with and with the carbon. With the carbon then, we're going to see then that carbon will have one of its electrons in this particular orbital as well. Okay, and so therefore then, this interaction here, which represents a straight line, you can draw a straight line through it. This interaction here between carbon and hydrogen, and let's go ahead and draw this in here in this manner here. This interaction here, this is a sigma bonding interaction. Just this is a sigma bonding interaction. Why? Because you have a line that you can draw straight through here, and the overlap here is for this single bond here, for the single bond between hydrogen and carbon here, is a single bond between an sp hybrid orbital from carbon and a 1s atomic orbital from hydrogen. It is going to be a sharing of the 2 electrons here, the sharing of the 2 electrons, which means that it's going to be a single bond, and therefore this single bond then is going to be a sigma single bonded atom, sigma single bond. Okay? Between carbon and hydrogen. Okay. All right, so how then can we explain this triple bond here? Okay, well, let's consider this here and make sure you keep this in mind. I'll finish up with this, that carbon has a second. Remember, whenever you have sp hybridization, you're going to have 2 sp hybrid orbitals, and so therefore carbon will have a second sp hybrid orbital. So this is the second of the, sorry, oh, sorry, let me go back here. This is the second of the sp orbitals. Okay. So this is the other sp orbital for carbon. Okay, now the bond that forms, now this is just 1 electron right here. Only 1 electron sits in that particular hybrid orbital. Okay, so 1 electron sits here, 1 electron sits here. So it can only form 1 bond. Okay, so it can only form 1 single bond here, 1 bond here. So it can account for 1 of these 3 here. And so how does